Navigators, this is 7.1, Modeling Situations with Differential Equations, and 7.2, Verifying Solutions for Differential Equations. What is a differential equation? Well, it's an equation that has a derivative in it, and the order of the differential equation is the order of the highest derivative involved in the equation. So again, parts to look at. It has to have an equation. It has to have a derivative. And we can see this one has a derivative. It's a second derivative. And over here, this is a differential equation. Again, it has a derivative. It has an equal sign. This is an example of a first order differential equation because it has a derivative taken once. And this is an example of an order 2 differential equation because it has a second derivative. Let me review some things that we've done in junior high: directly proportional and inversely proportional. Directly proportional, this is the proportional symbol. We can change a proportion into an equality by introducing the constant of proportionality. So this is a k, and what it'll do, it'll give a line. If k is positive, it'll be this line. If k is negative, it'll be this line. Inversely proportional, again, this is the proportional symbol. Inversely proportional sometimes is stated as proportional to the reciprocal. And in order to change a proportion into an equality, you have to introduce the constant of proportionality. When k is positive, it will be a picture in these two quadrants. If it's negative, it'll be in the other two quadrants. Again, direct proportional means that as x gets larger, y gets larger as long as k is greater than 0. When k is greater than 0, inverse proportion means as x gets larger, y gets smaller. Let's take a look at this differential equation and see if we can translate the words into math symbols. The rate of change of y with respect to x is dy dx. And proportional, this is the proportional symbol, to the product of t and the rate of change of dw dx. Now, to change this into an equation, we are going to have to introduce the constant of proportionality, which we will call k, and then this is t times dw dx. And that's all that we need to do on this particular problem. Let's take a look at this next problem. Again, we want to write a differential equation, and this part says the rate of change of the force with respect to the distance that the spring can open is inversely proportional, so it's 1 over, and it's proportional to the natural log of d. To change this into an equation, we have to introduce the constant of proportionality, which is k. So I'll put the k in the numerator. And then this will be the natural log of d. Now they're giving us some more information, and this extra information is going to allow us to figure out what k is. So they say the rate of change of f is 3, so this portion is 3, is equal to k, and then they say the spring has been stretched amount of 0.2. So when we solve for k, k will be equal to 3 natural log of 0.2, and now we can write the differential equation without the k in it because now we know what k is. And so this will be 3 natural log of 0.2 all over natural log of d. So that's our differential equation with the k being found. Let's take a look at, again, a differential equation, and let's find y. Well, finding y means we have to take an antiderivative. So this will be y is equal to tan x plus x squared plus 5x, and don't forget to put the plus c, because that represents all the solutions that have this derivative. Let's take a look at this next problem. It also has a differential equation that they want us to solve, but this time they're going to give us a point. So we are going to be able to find the c in this case. So y will be equal to e to the x, and then this will be minus 6x. We're going to go up a power and divide by that power plus c. And so the y is 0, and then e to the 1 is e, and then this will be minus 2 plus c. And so therefore c will be equal to 2 minus e. And so now we can write the particular solution. This is the one equation that has the point, this point 1, 0 going through it. And then we can put plus 2 minus e. And this is what we call a particular solution, because it's the one solution that has this point in it. Let's go ahead and do it again. We're going to solve for y. Y is equal to, and then e to the 2x, and then we have to adjust by multiplying by 1/2, and then minus 2x cubed over 3 plus c. And now we want to find a particular solution, so this will be 4 is equal to, when I put a 0 in there, that will be 1/2 plus c, and therefore c will be equal to 3.5, and 3.5 is 7/2. So now we can write our particular solution, which is 1/2 e to the 2x minus 2x cubed over 3 plus 7/2. Now, this next problem is exactly the same. It's just stated a little differently. A curve has this slope. So sometimes it says it that way. Instead of saying dy dx, it'll say the curve has this slope at each point. And what is the equation of the curve that passes through 0, 4? So again, same question asked in a different way. Let's take a look at solving a second derivative when we know two pieces of information. And I've already kind of done the whole problem, but I'll walk you through it. So this is the second derivative. Let's get to the first derivative by taking the antiderivative. And so I'll have this answer. And then I'm going to, this is my first derivative value at 2, so I put 2 right here, and I put 0 everywhere else, 1/2 plus c, so c is equal to 3/2. So now I have my first derivative, my particular first derivative, and then I'm going to find the antiderivative of that, which is this, but I'm going to have a plus c. And again, my y-coordinate will be 3/4, and I'm going to put a 0 in for all my values here, and I'm going to get c is equal to 1/2. And so here's my solution for what y is going through the antiderivative process twice. All right, let's take a look at finding the value of k of a function. This is a constant that's being multiplied, and we want to find it when we know the differential equation. So what we're going to do is we're going to take the derivative of this function and just regard k as a constant. So I'm going to take the first derivative, and e to the 2x, the derivative, don't forget the chain rule, is 2. And then the derivative of cosine is negative sine of 4x, and don't forget to take the chain rule 4 here. Now that I have the first derivative, I'm going to take the second derivative, which means I take 4k e to the 2x, that'll be the same thing, but don't forget the chain rule, times 2. The derivative of sine will be cosine, and don't forget to take the chain rule, which is 4. So I now have a second derivative, and what I'm going to do is I'm going to put that second derivative right in here. So that's what I've done. I put the whole second derivative that I have found, and I put it over 2 plus 8, and instead of y, I'm going to write what y equals. Y is equal to right here, all of this equals to 15 e to the 2x. Okay, now at this point, I'm going to, in front of you, go ahead and simplify. So this is 4k e to the 2x minus 8 cosine of 4x. And then I'm going to distribute plus 24k e to the 2x plus 8 cosine 4x, and equals 15 e to the 2x. And it looks like this and this will go to 0. And the number of these terms are going to be 28. So this will be 28k e to the 2x and then that's going to be equal to 15e to the 2x. Okay, and I know that this, since they're equal to each other, this part, the coefficient, and this part must be equal to each other because the rest is equal. So we're going to write 28k is equal to 15, and therefore k will be equal to 15 over 28. And that's how you find k when you know the function and you know its differential equation. Let's do that one more time. I have the function and I have the differential equation at the second derivative. So I'm going to find the derivative of this again. I found the derivative. Don't forget the chain rule in both cases. I'm going to take the second derivative. Don't forget the chain rule in both cases. And again, I am going to put the second derivative right in here. So that's what I have over here, 2 times the second derivative plus 18. And I'm going to take my y, and I'm going to put it in here, parentheses, equals 32 sine of the opposite of x. Okay, in front of you, I'm going to distribute negative 2k sine opposite of x minus 36 cosine of 3x, and then this is going to be plus 18k sine of opposite of x plus 36 cosine of 3x equals 32 sine opposite of x. And it looks like these are going to go to 0. And I'm going to count how many of these sine inverse x's I have. Negative 2k and 18k, so I'll have 16k altogether. 16k sine of opposite of x equals 32 sine of opposite of x. And then I'm going to notice that the part that's being multiplied to the sine is 16k. The part being multiplied to the sine is 32. So I'm going to set these equal to each other. 16k is equal to 32, and therefore k is equal to 2. So k is the value that will, and then I will have this second derivative or second order differential equation be equal to what I have here. And this is the end of the screencast.